is yours. Okay, you hear me? Is it on? Press this button. Okay. We have still to talk very loud about it, okay? So, that's it, yes. So I talked on behalf of the HENVI Forest team, and I'm actually trying to present a few results and a bit of the concept that are behind our project. And I have partial results, so I'm skipping quite a bit of steps that we've been doing to go into certain things there. Let's see if we're going on, yes. Okay. So, what I want to present here actually in terms of forestry was the kind of things that I'm using a kind of a matryoshka little doll. There's these Russian dolls, we have one doll, inside another doll, it's a kind of an analogy of how we are seeing things. So we can see things actually. There was some definition of this ecology of an important journal, Ecosystems, which defines ecology as the science of biological processes occurring at different scales. And I think the same thing of different scales actually we have inside this carbon sequestration and forest and carbon balance issues. So, what does it mean, these different scales? Let's a bit look on what is actually carbon balance, what is the whole picture there. So, basically, inside this HENVI project, what the natural science part is about, and I think that Laurie will talk to some extent about economic issues and other issues inside this system actually. It's actually the issue about climate change. And climate change is basically the sun warming up. What is happening here? So actually climate change is something about the sun warming up and the energy of the sun being trapped inside the atmosphere, like Marco was telling in the morning. And what's happening inside this atmosphere, there's actually several issues that actually forestry is influencing these things. The first thing is something like land use, like forestry, agriculture, managing forests, but also converting agriculture into forest, or forest into agriculture, and so on, which is one issue, which is running the climate change things. And this land use is emitting CO2. It's not the most important CO2 source, but when you talk about mitigation, we tend to talk about CO2 balances of forest and nothing else. But then there are actually also other issues. The CO2 is also coming from society, from our activities in society, like putting lights on, having an overhead projecting things. It's all emitting CO2. So what we're doing in society also emits CO2. And then there's something like interactions between land use and society. So I could give this presentation by handing out you a piece of paper and talking here without any overhead projector, and you would have a different CO2 emission. The CO2 emission wouldn't come from a carbon-fired or gas-fired power plant to some extent, but it would come from producing paper. So these things are affecting the CO2 emissions inside there. Then the other issue is actually that there's something like energy balance of forests. So the albedo, how much of the sun's radiation is actually reflected from the forest back to the atmosphere. So if you're flying from an airplane over Earth, you're seeing that there's something like dark forest and more light agricultural fields. This energy balance is actually to some extent important. And then the other emissions from forests, the NOx, methane, and VOCs, of which Ulle was talking, and from which actually Marco Kuhlmann was talking. There's the CO2 emissions which lead to the formation of clouds. So we have quite a complicated system. So I'm citing a bit Milne freely after Milne that I'm a little here with a very good brain and complicated diagrams are bothering me. So, and the same thing was actually occurring through all the history actually of climate change. When you go to this Kyoto things, that there's Kyoto Protocol and other protocols, and also the Durban Protocol, there's something like simplified versions of this diagram, which I showed before, which are going around there. There's these kind of boxes, smaller and smaller dots going down there, which are possibilities to make an idea about the impacts of forestry and climate change, which is somehow understandable for us. Which somebody, like a normal person like me, can understand. That it must be pretty damn simple to do that. Okay. The Kyoto Protocol approach is something like Kyoto Protocol approach, of which many people are talking, is basically mostly that only industry to land use exchanges. And actually, there's some possibility to include to some degree forestry into the Kyoto Protocol, but actually, for most of the countries, how we are managing the forest, if you don't massively overwashing the forest or massively protecting our forest, if we don't do something that is really radical, then actually what we're doing in forestry in Finland doesn't affect the commitments under the Kyoto Protocol, because there's a buffer around the net sink of the forests. And then you could actually take the forest sector, including industry, and then looking at excluding feed-based in society. You could take all vegetation impacts and looking at both industrial emissions. Or that there are actually many studies which look only at the forest carbon balance, how much carbon is in a forest compared to last year, or 5 years ago, or 10 years ago. And all these different things, all these different dots will have different volumes, different carbon sinks actually inside there. So actually we have a system which is, there's a certain problem in accounting for the carbon sinks and actually conceptualize the things. So, what actually I was wanting to talk about here a bit was slightly variable results, without very much final results. Actually, what is actually the impact that we are looking very carbon-centric on forestry? What are actually the impacts on talking about forestry only in terms of carbon? And that leads to the second question, which is linked actually to forest management. That if you're talking of forestry only, that we're only looking what is the carbon sink inside the forest. Are we doing the right decisions for climate change? So, if we only fix carbon in the forest, if we maximize the carbon sink in forestry, and we ignore what is occurring in industry, if we try to procure what is happening with emissions with albedo, emissions of VOCs, and other issues, are we making the right decisions for climate change? Or are we doing something which is wrong because we are artificially simplifying the system? Okay, once I talked very much against carbon, let me start to talk about carbon again, indicated by this black and white ball. So, if you look at carbon, when you remember Marco Pulman's presentation in the morning, you actually find that carbon is the most important greenhouse gas. And it is actually limited for industrial activities and then from land use changes, including forestry. And actually land use changes, especially tropical deforestation, are a relatively important source of carbon dioxide. And source of carbon dioxide. It seems that forests also are a very important sink of carbon dioxide. So if you talk about emissions from land use changes, you're talking about 1/3 of the emissions, and then there's something like 1/5 of the carbon sink actually, which is well, let's say 1/5 to 1/10 of the global carbon sink, which is somehow attributed to forests, which allows a very pretty large uncertainty. And then you could say that actually emissions from forests are relatively large, but they are probably expected to be relatively comparatively small in something like forests which are under stable management, as European forests and Finnish forests are. Okay, so I started with something like the first kind of simulation, and this is the carbon, this is the life transect actually of a forest, of a spruce forest. The green line here is actually showing the woody biomass in kilograms per square meter. So the biomass in the biomass, actually, wood and needles and other things. And the black is the whole carbon stock inside the forest, how it develops with the stand. So here at the beginning, you start at age 0, you have the old stand, which is 190 years old down, which you cut down. You're creating something like that. The carbon stocks are reduced in both the soil, which is the difference between these two, it's the vegetation, because the trees are away. And then it's growing back again, it ends up at approximately the same level as initially. And that's pretty much the same thing actually, like the things that actually Jan has been showing. And we have these things that actually, what indicate by these two lines is actually that when you look at the carbon stocks, the main tool in forestry for changing the carbon stocks inside the system is changing the rotation time. So rotation time is the time between cutting the forest once, which is here assumed for this line, which is assumed to be at 90 years. This is the average carbon stock at 90 years. And here it's another line where we assume that we have a short rotation of 50 years. So if you shorten the rotation, as it would do, it would grow bioenergy. It would reduce actually the carbon stocks inside the system, even without taking into account carbon depths, carbon stocks inside bioenergy. But we would get energy from that. Okay, then the second component inside this HENVI project was something like albedo. Albedo is actually the thing that if you have been walking on a parking lot out of black asphalt in the summer, it's actually the effect that you feel there. So albedo is something like short-wave radiation, light is coming from the sun, and when it hits the dark forest, the dark surface like forest, it is absorbed and converted into long-wave radiation, which is heat radiation converted into heat which stays inside the atmosphere. And therefore something like a black carbon wood and something like a white snow surface have very different albedos and very different effects in the spring, for example, temperature, indicated by these small design black microscopes inside there. And then you could think that actually a large proportion of the short-wave radiation is going back through the atmosphere. It's lost to space, it's not keeping us warm inside here, which might be a good thing when you think of climate change. But long-wave radiation is remaining in the atmosphere. It will warm up the atmosphere. And this is an advertisement that Marikeski also has made a wonderful video installation in the poster session, which is about the albedo rover. And this is a picture from this video presentation. Inside there. And now, what you have is actually inside there is a different, here is the x-axis, it's the date of the year. And this is albedo is measured from MODIS, from the MODIS satellite particular area. And you have different land use types, pine forest, spruce forest, and other things. What you see is actually in the winter, you have large differences, especially between open areas and coniferous forests. So open areas tend to be much lighter during the winter, physiological. And this difference is actually, to some extent, continuing during summer. So you have pine forest and spruce forest down here, and you have deciduous forests and croplands, for example, upstairs. So you have these differences inside these different land use classes and different things. This is from a publication of Mea Kubik and Erwin Tombo and me, actually. And here's a kind of a picture, actually, how we are thinking that this albedo feedback is changing there. So we are assuming here that something like a birch forest, which is the lightest forest, has a radiative force. So it's not warming up the atmosphere. So albedo is flowing. It's a kind of flowing thing. Every surface will warm up the atmosphere compared to no surface, to no surface at all. Oops. But so we put here a point to 0 for the birch forest, for the open area of the birch forest, and for a birch forest it seems that the albedo doesn't change very much with age. But for a spruce forest, This will change with age and volume over time. It will come up if you calculate that if you're changing 1 square meter of forest, you're growing 1 square meter of forest over time, then the radiative forcing would be similar. That you would put something like a heater with 1.2 at the power of 10 minus 14 once per square meter. You put such a kind of a heater to each square meter of the Earth. So you think that you have a very, very small heating effect for overall of the Earth. But actually, the heating effect for carbon is also very small. So you have to look at it on the scale of the surface of the whole Earth. Inside there. Okay. Then the next point was something like the VOC and radiative forcing, a bit continuing on Marcus' thought that forests are emitting something like volatile organic compounds, which lead to the formation of aerosols, which are absorbing and reflecting light from the atmosphere. So they actually have an effect on the temperature, the radiative transfer actually of the aerosols itself. And then actually they also lead to the formation of clouds, which may, depending on the cloud type, to make things more complicated, may warm up or cool down the atmosphere. It seems that the main effect is actually that they're cooling down the atmosphere. But this is a relatively complicated, physically complicated solution, which is something where we are doing really work-breaking new work inside this HENVI project, which isn't totally ready yet. And what we are doing for this is that we are using the so-called SOSA model, which is a model of VOC emissions and meteorology. You're building up something like aerosols in chemistry based on emissions of different volatile organic compounds. And you're making aerosols, and you're looking at the moment on the direct aerosol forcing. So they're excluding everything which is cloud formation at this moment. Okay, and the results here, to make another advertising break, is presented a bit more in detail and posted by Peter Morgensen, Lisu, McAvoy, Tom Kalios, Animana Talo, and Jana Beck. And here we focus actually a bit on the time simulations inside there. So, what we try to look at is we actually try to make simulations for different time forests, 20-year time forests, 50-year time forests. And the minimum campaign emissions, so the emissions of the most important VOCs, there are different species of VOC in the emission inside the scenario. They actually increase if you increase the biomass of the forest. If you increase the green biomass inside the forest, they will increase from 15 to 30 by 400% approximately. And they will increase another 20 to 30, other 30% when you're going from a 20-year forest to a 40-year forest. And we did it for two different times. We did it for 2010, and we did it for the climate 2050 inside there. And what we have is something like relatively large increases in the VOC emissions. And then we have also large increases with these errors, which cause something like increases in emissions with climate change. And then inside the SOSA model, you can calculate something, you can simulate what is the formation of aerosols inside this model through nucleation and other processes. And what we actually found there is that this is to some extent more also climate driven and other things. So actually found that there were very small effects of changes in aerosol at this moment inside the things. It seems to be that there's something like a change in the aerosol size distribution, right, which seems could be quite important for cloud formation and other processes. And there's something like a large increase in aerosol formation when you go across the climate, different climate scenarios inside there. Okay. Then, so what we find is that actually changing rotation time inside forests will not change very much the cloud formation and the formation of aerosols, but then actually changing climate will do that. And there are something like other processes, like other emissions of those substances involved inside there. This is something like a complex input which includes assumptions about how climate will change and how society and other emissions from the society will change. Okay, then we're going to the next point, which is storage of carbon actually in tree and wood products. So let's give this kind of conception, especially in category which is not without reason grounds for its forestry, that we're actually increasing the amount of carbon in all kinds of wood products, and this would be a very important store over time. Now, when we come to most of the empirical studies, they find actually that very few, the amount of wood, something like long-term life projects like this beautiful table over here, is relatively limited. That most of the wood products have lifetimes which are unfortunately relatively short. So we have this HENVI, for example, this wonderful HENVI program. I'm not very sure if this program will be in a bookshelf in 4 years' time still, or if it will go down the way for recycling. Sorry for insulting you. Yes. But you could think that actually complex issues of which we don't know very much as foresters and ecologists, like recycling and use, actually determines the total impact of wood products. We took a kind of a publication from Cardialine in 2004. We took a kind of a decomposition product. This has actually two different kinds of products. It has something like sawlogs, and then something like the other industrial wood, which is used for papers and other things. Here's assumed assumption that we have one cubic meter of wood, something like that at the beginning. How much of it is left actually there? What you find there is actually that for sawlogs, the turnover time is around 20 years, or about half of it is left about 20 years, and then for paper products it was something like 7 years. So we're talking about times, residence times of most of the wood products inside the product wood, which are relatively short, and relatively short if you compare to the residence time of wood inside the forest. So if you would go to protect the forest, and the same trees would probably still be there for a long time, even if you protect something like a very old stand, which is close to fall down anyway. So, and here's actually when Jan Gerhana was presenting a kind of like a very optimistic figure, what happens with sawlogs over time. Here's a kind of pessimistic version of it actually. This is the HENVI simulations using the parameters that they use for a spruce forest in Finland. And here's a green thing, is the wood in biomass. The difference in between here is also the thing which is now, it's the wood inside the soil. So the total stock inside the forest, the amount of carbon that will find inside the forest is below this, the sewer line. And then the red line is the difference between these two lines is the amount of carbon which is stored inside the wood products. And this shows that there's something, a large pools, large changes inside there, which decompose over time when wood is retired from the garden stuff. But this kind of analysis is pretty difficult because wood has different uses, different things. It depends very much on things like our consumption patterns. So if you put wood into a log house, almost all of it will be there in 40 years. If you put it into moldings, if you put sawlogs into moldings for making building a house in cement, then they will be gone after 1 year or 2 years, even if we talk about sawlogs and other things. Then the other kind of issue which we have there is the question of looking at different lifetime of things. Look at those which stay there for a long time, and those which are running away very fast. So if you have albedo changes, then if you change and cut down the forest and change the albedo, the benefit of the carbon. The benefit, if you change the albedo of the forest, and the benefit of the albedo or the damage of the albedo will be done instantaneously when the albedo is changing. When I breathe out here, then the carbon which I emit to the atmosphere will stay there for a certain time. So we have to make an assumption about what is happening to the carbon which we emit to the atmosphere. Maybe using a kind of an atmospheric, ready-made atmospheric model actually to look on carbon sinks inside the atmosphere, which assumes that if you emit 100 carbon, the amount which will remain in the atmosphere of it will a bit develop like this. And then we tried to do this kind of simulation and come down to something like radiative forcing, and calculate the radiative forcing over time. So this is actually these things converted the carbon into radiative forcing. So you converted the carbon and how much it is heating up the atmosphere each time in the world globally. And then we added the albedo to it. So the black line is carbon inside the forest and now the blue line is the carbon inside the forest and the wood products. And the black line is you take into it the albedo effect into it. This is the kind of rotation time inside the forest. It's a temporal development of this. There's these inconsistencies in the line which comes from the different things. So we are simulating one single stand over time, which is sitting over there. And inside this HENVI project, we have the idea to go to larger areas and other things. So basically, we think that actually this albedo effect has a certain effect inside there. The VOC effect seems to be at this moment relatively small. I think they will become much bigger if you take cloud formation and these processes into it. And then also the VOC effects have strong interactions actually with climate change, which is not included here. This is under current climate. And there seems to be some difference if you go on to further things. So, the other things that we are missing actually is that one is something like the substitution effect that Jan Bernard has been talking about. I think I'll kind of small talk about it also tomorrow, and I think Lau will also talk about it. There is something like bioenergy use of wood inside there. And there is something like peatlands. Peatlands are important sources of methane and NOx, and there seems to be a certain feedback and certain trade-off also between you can choose what kind of emissions we have from peatlands. So if we drain peatlands as many peatlands in Finland are now, you will have something like long-term emissions of CO2, but less emissions of methane and NOx. And if you restore peatlands or protect them, you will have more emissions of methane, so you can choose between the devil and the blue and the black. What was it? The devil and the blue sea, basically. And here's an example from peatland things from a slide from Berninger. He's been looking on carbon balances for actually pure grey forest, which is a sink of CO2. Then there's another forest which has a similar actually stat structure, similar amount of wood body into it, which seems to be something like a source of CO2, depending on how fast actually the peat below the forest is decomposing. And then there's something like other surprises also, from a research from Berninger and Berninger and other authors which I don't remember, and it shows actually that the white points are CO2 emissions from places where logging residues have been left on the peat, and it's actually the emissions from decomposition of the peat, and then the black points are decomposition without logging residues inside there. And then we talk about something like the priming effect, that actually trees and vegetation have effects on decomposition processes inside the ecosystems, which are not taken into account by current models of carbon cycle inside forests. So there are something like lots of surprises coming forward to this project, and I hope that we can do something like a final seminar in 2 years' time, that we can come up with something like that. But I think that the kinds of conclusions that we still have, something like carbon, something and it's a minor main effect. But actually, in carbon seems to be the point effect. But the other effects of albedo are quite, like albedo, are quite important. And main effect actually is the total climate change effects of forest management. And may turn actually balances between having different management options actually inside there. So actually the albedo tapped inside the forest that was calculated in a certain way for a pessimistic case in southern Finland. If you go to other forest systems, albedo effects might be larger. Then the other effects as carbon storage in forests, the effects of peatland drainage, and other effects might be actually quite important and affect actually what is the best management for the forest in the future from a climate change point of view. And there are of course all the complications inside there which we will do in the socioeconomic research that carbon and wood are not the only products that we're getting out of the forest. I like to go to the forest and pick mushrooms, and I don't want a forest that fixes carbon and doesn't produce mushrooms. Okay, I leave the floor for the discussion. I think that.
Okay, thank you very much, Frank. We have time for a few questions.
Yes.
One correction and one question. It's actually the sense of carbon dioxide is most important greenhouse gas, but in fact it's only contributes maybe 1 to 2%. It's actually water vapor is most important.
Okay. Yes, you're right.
Exactly. This is amplifying, there is water pollution and so on, and this is actually the least. It's not 2%.
Yes.
But I think it is just I think you know how it works, but it's just like that. But the other question was, you had like huge increase in VOC emissions in 5 years' time. It was like 15 years old and 20 years old, forest, and it was like 400 to 500%. But it's generating this huge increase.
It's the changes in the tree biomass.
In 5 years' time?
Tree, yes.
Oh. Okay.
It has been calculated using the emission factors for the Megan model for the emissions, and then current climate data for 1 year in New Zealand, I don't remember which year, and then the biomasses which are predicted by our model for these different years. About the water vapor, I think yes, you're totally right. I think there's no possibility actually to manage water vapor inside the forest. Perhaps we should consider building something like really huge humidifiers or something like that. But you're right, yes.
Okay, thank you. More questions? The final one then.
Tuomas Lin from VTT. Could you go back to the slide 23 where you showed the albedo and carbon impact? So this one here.
Yes.
Could you have a guess or estimate or some kind of estimate on how this would change if you could include the VOC emission impact to clouds? And if you could you give some suggestions how to manage forests or not manage them or deforest, or if you want to optimize the climate impact of the VOC, what would you do with the forest?
You're asking the difficult questions, okay? Okay. So when you look at the VOC impacts of forests and to manage them, I think there's a trade-off, I think. I think there's a trade-off of VOC there's a trade-off of VOC with albedo. So albedo will decrease. The effect of albedo will be more climate warming if you increase the biomass, while VOC emissions will usually increase the things. Now, what we have there is that probably will increase cloud formation if you have the VOC, but actually we don't have any idea if this will be totally unimportant, moderately important, or very important. I think we are totally in the dark on these issues. if you look at the VOC emissions in Mark Pullman's presentation, there was this large error bar on the human effects of climate change, and of this error bar, probably half of it at least was coming from the VOC and the potential VOC impacts. So basically, I would think that if you have more VOC emissions, you will have higher cooling effect aerosols in albedo. So you should take the forest properly, do small thinnings, do small disturbances from time to time to go into Ulo's presentation, to keep the forest stressed and keep VOCs flowing out of the forest. But I hope that we can come up with something which is better actually towards the end of the project, that we are pretty much in the down project supporters of it, unfortunately. Or that's the interesting thing. That's why we are here. One of the reasons why we are here.
Okay, thank you. We have to stop this morning session now, and I thank all the presenters and all the participants.